So hi everyone, today we will be discussing igneous rocks. Igneous rocks are formed as magma or lava cools and crystallizes. Magma is the molten rock that is often generated by the melting of rocks in the Earth's mantle. Once formed, a magma body buoyantly rises towards the surface because it is less dense than the surrounding rocks. When magma reaches the surface, it is called lava. Sometimes, lava is emitted as fountains produced when escaping gases propel molten rocks skyward. On other occasions, magma is explosively ejected from vents, producing spectacular eruptions. Okay. Now we have crystallization. Crystallization is the process of solidification of ions of magma and lava in an orderly pattern. So technically, crystals or minerals will be the products of this process. Okay. The rate of cooling affects the crystallization. Okay, the rate of cooling strongly influences the crystal size. If magma cools very slowly, ions can migrate over great distances. Consequently, slow cooling results in the formation of fewer larger crystals. On the other hand, if cooling occurs rapidly, the ions lose their motion and combine quickly. This results in a large number of tiny crystals all competing for available ions. Therefore, rapid cooling results in the formation of solid mass of small intergrown crystals. Now we have the two types of igneous rocks. When molten rock solidifies at the surface, the resulting igneous rocks are classified as extrusive or volcanic. On the other hand, when magma loses its mobility before reaching the Earth's surface and eventually crystallizes deep below the surface, the igneous rocks that is formed is termed intrusive or plutonic. Intrusive igneous rocks remain at depth unless portions of the crust are uplifted and the overlying rocks are stripped away by erosion. Okay, so again, we have the extrusive or the volcanic igneous rocks that solidifies at the surface. The rate of crystallization is rapid, and this one will produce numerous but smaller crystals. On the other hand, if we have intrusive or plutonic igneous rocks, the magma will solidify before reaching the surface, and the rate of crystallization is slow, thus producing fewer and larger crystals. Okay, now we have the composition of igneous rocks. Igneous rocks are composed mainly of silicate minerals. Chemical analysis shows that silicon and oxygen are by far the most abundant constituent of igneous rocks. These elements, ion plus, the ions of aluminum, calcium, sodium, potassium, magnesium, and iron make up roughly 98% by weight of most magmas. In addition to that, magma contains small amounts of other elements including titanium and manganese, and trace amount of rare elements such as gold, silver, and uranium. So now we will be tackling the dark silicates and light silicates first before discussing the composition of rocks into basaltic, granitic, andesitic, and ultramafic. Okay, let's start with the dark silicates. As magma cools and solidifies, these elements combine to form two major groups of silicate minerals. The dark silicates are rich in iron and magnesium and have comparative low silica content. Olivine and pyroxene amphibole and biotite mica are examples of dark silicate minerals of the Earth's crust. By contrast, light silicates contain greater amounts of potassium, sodium, and calcium and technically are richer in silica than in dark silicates. Light silicates includes quartz, muscovite mica, and the most abundant of all mineral groups, feldspar. Feldspar make up at least 40% of most igneous rocks. Now, let's talk about the granitic and basaltic composition of our rocks. Geologists refer to granitic rock as being felsic. This one is a term derived from feldspar and silica. In addition to quartz and feldspar, most granitic rocks contain about 10% dark silicate matter, and usually this one are biotite mica and amphibole. Granitic rocks are the major constituents of the continental crust. When you look at granitic rocks, so this one has lots amount of silica and sodium and potassium, but this one has lower content of magnesium, iron, and calcium. and technically this one will melt at around 650 degrees Celsius. Now let's move on to the basaltic composition of our rocks. Rocks that contain at least 45% dark silicate minerals and calcium-rich plagioclase feldspar, but no quartz, are said to have basaltic composition. Basaltic rocks contain a high percentage of dark silicate minerals, so geologists often term them as mafic, which came from the word magnesium and ferrum. Okay, because of their iron content, mafic rocks typically are darker and denser than granitic rocks. Basaltic rocks make up the ocean floor as well as many volcanic islands located within the ocean basin. Okay, so when you look at the basaltic composition, this one has low silica content, low potassium and sodium content, but this one has high ferromagnesian minerals and technically has higher temperature at which meltings begin. Okay, now let's move on to the andesitic and ultramatic composition. Okay. Rocks with a composition between granitic and basaltic are said to have andesitic composition or intermediate composition. This one is after the volcanic rock andesite. Intermediate rocks contain at least 25% dark silicate minerals, mainly of amphibole and pyroxene and biotite mica group, with other dominant mineral being plagioclase feldspar. Okay, when you look at andesitic, so this one contains around 55 to 65 silica content, and this one is in the middle. Okay, now we have the ultramatic composition. Another important igneous rock is peridotite, which is mostly composed of olivine and pyroxene, and this one falls on the opposite side of the granitic rocks. Because peridotite is mostly composed of entirely ferromagnesian minerals, its composition is referred to as ultramafic. Although ultramafic rocks are rare in Earth's surface, peridotite is the main constituent of the upper mantle, and this one is mostly made up of olivine. Okay, the next one is the texture. So geologists describe the overall appearance of a rock based on the size, shapes, and the arrangement of its mineral grains, and technically this one is the texture. Texture is an important property because it allows geologists to make inferences about a rock's origin based on observations of the crystal size and other characteristics. Rapid cooling produces small crystals, whereas slow cooling produces larger crystals. As you might expect, the rate of cooling is very slow in magma chambers that lies within the crust, whereas a thin layer of lava extruded upon the Earth's surface may chill to form solid rock in matters of hours. So, and small molten blobs ejected from a volcano during a violent eruption can solidify in mid-air. Now I'm gonna discuss some example of texture with you. So this one includes fine grain texture. We have coarse grain texture. For pyritic, we have vesicular, we have glassy, and we have pyroclastic texture. Okay, so let's start with fine grain texture. Igneous rocks that form at the Earth's surface or as small intrusive masses within the upper crust where cooling is relatively rapid exhibit a fine grain texture. By definition, the crystals that make up fine grain igneous rocks are so small that individual crystals cannot be distinguished and can be distinguished only with the aid of a polarizing microscope or other sophisticated techniques. So therefore, we commonly characterize fine grained rocks as being light, intermediate, or dark in color. Okay, so these are my examples. So for granitic composition, we have rhyolite. For andesitic, we have andesite, and we have basaltic, and the example is for basalt. Okay, so moving on, we have the coarse grain texture. So when large masses of magma slowly crystallizes at great depth, okay, they form igneous rocks that exhibit coarse grain texture. Coarse grain rocks consist of mass of intergrown crystals that are roughly equal in size and are large enough so that individual crystals can be identified without the aid of microscope. Geologists often use a small magnifying lens to aid in identifying the minerals in a coarse-grained igneous rocks. So these are my examples. For granitic, we have granite. For Endocytic composition, we have Diorite. For Basaltic composition, we have Caprol. And we have Ultramatic composition, we have the Peridotite. Okay, moving on, we have the porphyritic texture. Different minerals crystallizes under different environmental conditions. It is possible for crystal of one mineral to become quite larger before others begin to form. If molten rock containing some large crystal moves to a different environment, the remaining liquid portion of lava cools more quickly. The resulting rock, which has larger crystals embedded on a matrix of smaller crystals, are said to have porphyritic texture. The large crystals in a porphyritic rocks are referred to as phenocryst, and then the matrix will be called ground mass. So, as you can see in the picture, I have here some examples. Let's take granite porphyry, for example. Granite porphyry here, the feldspar or the color brown here is the phenocryst, and technically the ground mass is composed of mica, and we have quartz. Okay, so for example, for andesitic composition we have andesite porphyry, and for basaltic composition we have basalt porphyry. Okay, now moving on, we have the igneous rocks. So we have vesicular texture. Common feature of many extrusive rocks are the voids left by gas bubbles that escape as lava solidifies. These nearly spherical openings are called vesicles, and the rocks that contain them are said to have vesicular texture. Rocks that exhibit a vesicular texture often form the upper zone of the lava flow, where cooling occurs rapidly enough to preserve the openings produced by expanding air bubbles. So these are the examples. We have the pumice and we have the scoria. Okay. Next one, we have the glassy texture. During some volcanic eruption, molten rock is ejected into the atmosphere, where it is quenched and cools quickly to become solid. Rapid cooling of this type may generate rocks having glassy texture. Glass results when unordered ions are frozen in place before they are able to unite to form an orderly crystalline structure. Obsidian is a common type of natural glass, and this one has a similar appearance to dark chunks of manufactured glass. So obsidian is our example. Okay, and then we have the last one, the pyroclastic texture. Another group of igneous rocks is formed from the consolidation of individual rocks fragments ejected during explosive volcanic eruptions. The ejected particles might be very fine ash, molten blobs, or angular blobs torn from the walls of a vent during an eruption. Igneous rocks composed of these rocks fragments are said to have pyroclastic texture or fragmental texture. A common type of pyroclastic rock is a welded tuff, and this one is composed of fine fragments of glass that remain hot enough and eventually fuse together. This picture here shows, okay, our rocks with different types of textures and where to find them and how are they formed. So this one is the end of our igneous rocks topic. So I hope you learned a lot. So I'll see you in our sedimentary rocks topics next time. Thank you.